Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, so we're happy to have Sergio's third talk. A little rationality goes a long way.
Yeah, that's what, yes. So when I start with this slide, I always say, that I come from the center of rationality, which you know where it is located, yes? Jerusalem, that's really the most rational place. Okay. So now, yeah. Okay. Okay, so I want to start with, okay, so the good news is that that's my last talk here. I don't know. Yeah. And so what I'm going to do is talk a little about communication complexity, which is in some sense a continuation of what I talked last time, and in other senses it's not, but I'll remind you what is needed, and that will naturally flow into correlated equilibria, and then I'll switch to the other thing, which is dynamics, correlated equilibria, and adaptive heuristics, and other stuff. And again, time depending, we'll see what we do. So this is joint work with Ishai Mansour that many of you know. Everyone knows, probably. Okay. Okay, and I stole this presentation from him, which means that all misprints, unlike yesterday, I'm not responsible for. Yesterday I was responsible for all the misprints, and there were too many, yes. Okay, so, okay, which also means that may not be exactly the way I will talk about, and so we have an equilibrium concept in game theory, like Nash equilibrium, for example, which is a static concept, okay? And the question is what are the dynamical aspects? How is such an equilibrium reached? Okay. Now let me remind you the notion of uncoupled dynamics. Okay, which says the following: that when you start, so assume that you have a game that is repeatedly played. Okay, and the initial information of every player is only his own payoff function. Okay, so I know my own payoff function. Yuval knows his own payoff function. I do not know Yuval's payoff function. Okay, just an information restriction, which is quite natural. If you think of payoffs as being, even if I know the outcome, I have no idea how Yuval evaluates those things. I don't know anything about his utility function. I mean, I hardly know my own utility function, to tell you the truth. But let's assume that I know my utility function. But assuming that I know Yuval's utility function or somebody else, that's really a very strong assumption. And in fact, almost every dynamic in the literature, or almost every natural dynamic, is uncoupled. So what happens is that those dynamics, the way they operate, there is a state, what people are playing, what I played in the past, what I'm playing now. As a function of the state, I decide what to do next. And I decide what to do next as a function of my payoff function, depending on my payoff function, not depending on the payoff function of somebody else. Okay? So for example, a best reply kind of dynamic, I'm taking the n tuple of strategies being played, and I'm playing a best reply to what the others are doing. Again, that's uncoupled because it only depends on my own utility function. Okay, so now to see that you understand. Give me a dynamic which is not uncoupled. It's hard, huh? It's hard.
Directly to the mesh.
Very good. Or maybe, go continuously to the next, doesn't matter. But that means I have to take the game, which means the n tuple of utility functions, compute a Nash equilibrium. If there are many, decide on one of them one way or another, and then have a dynamic that goes directly there. But you cannot do it, I cannot do it knowing just my own utility function, because my own utility function does not determine the Nash equilibrium. For this I have to know somebody else. And in fact, if you try thinking about, there are...
You're producing threats, right? If I threaten the opponent to do something that's very bad for his utility function, knowing that, so I pull towards an area that's bad for him, and the only way for him to get out of it is to pull towards an area that's good for me.
Very good. So as you see, this is quite sophisticated, right? That's sophisticated behavior. So when you decide what to do, knowing what his utility function is and how you will do and so on, that's quite no. I mean, that's not an that's not a negative comment. This is not a negative comment. Yeah, it's not a negative comment. What I'm trying to say is that simple dynamics will be uncoupled. Sophisticated dynamics, sure, I can start thinking, what Yuval will do and what Yossi will do and so on and so on. But
neighbors are uncoupled, but dogs can already.
Yeah. Okay. I may use it. Okay. Okay. So uncoupled dynamics, the starting. So now in informational, again, this is an information assumption. Has nothing to do with optimality, rationality, or anything. It just that's what I know. And as I said, this is very natural okay. So now, of course, I can learn. So that's the initial state. I can learn from what Yuval does. What his utility function might be. I'm never sure, but I may learn. Okay, now related notions, well, you distributed, that's something that you are well aware of, right? When each computer or whatever, I don't have to explain to you, yes. Privacy preserving is a parallel notion in mechanism design, again, where you only use your payoff function. Decentralization, various decentralized notions, again, have this nice property, okay? Okay, now, for correlated equilibrium, there are nice uncoupled dynamics that converge to it, and that, in fact, I'm going to talk about that in the second part. So I can just go over this fast. So all this regret matching that I hinted last time, and I will spend some time on this today, and there are lots of other things. There is also Foster and Vora, which in fact came before all this literature, which are not exactly in this class. They are different kind of dynamic because they look at forecast, at calibrated forecast, and then best reply. But in some sense, they are still uncoupled dynamics. Okay, not in some sense, they are uncoupled dynamics. Yes. Okay. Now all these dynamics converging to correlated equilibria do this fast, which is polynomial time. You get within epsilon in rate of convergence 1 over square root of t. Payoff functions can be arbitrarily, and they are also simple, as we'll see later. Okay? How about Nash equilibria? So now I want to know, can we find the nice dynamics converging to Nash equilibrium? Okay? Can we find simple uncoupled dynamics that converge fast? Okay? Now, the results I talked about last time, again, just hinted, is that if we take deterministic continuous time dynamics for games that have a unique Nash equilibrium, the answer is it's impossible. You cannot find uncoupled dynamics that are guaranteed to converge to Nash equilibrium even when it is unique. Okay? So it's hard. On the other hand, it's hard if you are in this setup, namely if you are looking at deterministic continuous time. But if you are willing to be a little more, for example, more than flexible, you have to really bend backwards and forwards. Okay? In fact, what you really have to do is to start doing exhaustive search. Okay? So if you start looking at stochastic dynamics, there are various things that work. Yes? So deterministic calibration, hypothesis testing, regret testing. Those are things of the sort, all these testing things. Can you see this red dot? I hardly can see it. Okay. So all this. Your
hand is pointing.
Yeah. A stick is always much better, but I guess that's old technology. Yeah. No, in the cellular rationale you have a big stick, and at the end I put a red tape, so you have the red dot. It's like this. Have you seen this video of the Japanese people playing? You must have seen that. Ping pong, right? Have you seen that? It's a great. You haven't seen it? Where do you live? You're at. Nobody knows what I'm talking about? Okay. Then I won't spoil it for you. Okay, so all this testing is something like hypothesis testing, and those are very complex dynamics of the sort where you try to very carefully equilibrate probability of error of type 1 and type 2, and they only lead you to Nash equilibrium 1 minus epsilon of the time, but you are never going to stay there forever. You are always going to leave it and start searching again. I mean, getting to Nash equilibrium is tough. That's what we learn from all this literature, okay? And so they are all in one way or another, something like exhaustive search. Stochastic, deterministic, whatever. It's, okay? Now, the question is this a deficiency of the existing literature? I mean, it's just that people weren't smart enough to find nice dynamics that go nicely to Nash equilibrium, and they could only find all these very complex dynamics, okay? And what we're going to show is that, in fact, there is no escaping exhaustive search. Dynamics that converge to Nash equilibrium will take a very long time to do that, okay? And we are going to prove that as a consequence of the amount of information that has to be transmitted between the players. In order to reach Nash equilibrium, where each one only knows, okay, so let's, okay, perhaps I'll, yeah, so let's jump to, okay, let's jump here to understand what the setup is. So the setup is that initially every player knows only his own utility function, payoff function, okay? So that's the initial information. Each step, every player performs an action, and they observe everybody's action, okay? So that's information that goes in between them. That's a communication in between are just actions being played, okay? Now, a Nash equilibrium procedure is going to end with one of two things. Either all the players knowing a Nash equilibrium, or at least each player knowing his own action in a Nash equilibrium, or, remember, this, if we are talking about pure, that means pure Nash equilibrium did not exist. It may end up with everybody knowing that there is no pure Nash equilibrium in that game. Okay? So that's a communication setup. Now, to make this a little more precise, I don't know if I'll need all these things, but so we have, probably I don't need them. So we are just going to talk about binary games, simplest possible setup. So we have n players, so that's a thing that is going to go to increase. So everything will be a polynomial or exponential in n. So every player has just two actions. So joint action is 0, 1 to the power n, so an n tuple of bits. This is the payoff function. So for every n tuple of bits, which are the actions of the n players, there is a payoff to player I, and that's a game. Okay? And I don't have to tell what I will be. Okay? Now, the communication complexity, I mean, I guess that here I don't have to explain what that is. Okay? You have a certain procedure that has an input, has inputs, and generates an output. And the question is how many bits of communication have to go through, have to be transmitted between the participants until they reach the final result. So they want to compute a function or something like this. That's the usual setup, right? Everybody knows that, yes? Somebody doesn't know it.
What?
Even after I explain it now, you mean? I just explained it.
Less than so what you said, actually, if you could say that.
Sorry? So the general setup is, say you have two participants, yes? Or you have n participants. Each one has an input, okay? And you want to compute a function of those n inputs. And at the end of the procedure, each one of them has to know the value of the function of the n inputs. Okay? So the question is, now there are many ways to compute functions, right? The question is, what is the best way to compute? And we don't care about computation costs. That's important. We only care about communication costs. So we have to know how many bits of communication have to go between the players until they reach the common value of that function. That's communication complexity. So it's a minimum of all procedures such that they end in, et cetera, standard definitions. Even I can understand that. So it's, okay, so each agent has an input, each player has an input, which is the payoff function, only his own. Okay? They need to compute an output, which is a Nash equilibrium, pure or mixed, depending on what we want. The communication proceeds in rounds, where in each round, each agent plays an action. So that's just one bit of communication. And the complexity, the communication complexity, is the number of bits that are being sent. So if you want to count bits, it's a number of bits. If you want to count rounds, how many? Then you have to divide by n, because there are n bits each round. So that doesn't matter, since anyways things will be exponential. Okay. Okay, here are some nice pictures on how you compute lower bounds and so on. I won't tell you about that because that's communication complexity. You can read, there is a nice book of Noam Nissan and Kushilevitz, right? So you can see all these nice things if you're interested. Okay, so there is Probably it's the first, almost like the first example of a nice function, the disjointness function, for which, so player 1 has an input S1, player 2 has an input S2, and you want to know which are subsets of an m-dimensional, of a set of size m, and you want to know whether the two sets are disjoint or not. Okay? And how long does it take? Then the answer is 2 to the power m. Okay? That's a lower bound, an upper bound. That's a nice result. In fact, quite easy if you start thinking about. There is no way to find if the two sets. So I know S1 and Yuval knows S2, which are two subsets of this of 1 up to m. Okay? And we want to find out. So one way is that I'm going to tell Yuval exactly what my set is, and he's going to check if there is a common element or not. Yes? And you can't do much better. Sorry.
I mean,
it depends on
The number of bits that have to be transmitted. Now,
yeah, you just
it's
need to
n. Okay.
You just need to know to let
to know one set.
Yeah, you need to know a bit for each element. There is an exponential blow up here. I mean,
Right, you are right. That's why I said, right, because our m is going to be 2 to the power n. And that's why it's 2 to the power n. Okay, that's correct. Yes.
But the number of bits, okay.
The number of bits is going to be m. Okay? Okay. Anyway, I don't want to go into details of this because it's not, I mean, the details here are not very important. I'm sorry, but at least from my point of view. You know, so there is a reduction, the standard reduction. You take the problem of finding pure Nash equilibrium in a certain class of games, and you reduce it to the disjointness problem. So if you could solve that quickly, then you'd have solved the disjointness problem quickly. You can't do that, so you get a lower bound, which turns out to be, okay, here, sorry, I'm missing a theorem here. Oh, there is a theorem. Okay, so. But it's not, okay, sorry. As I said, those are not my slides, so I'm, my excuse. So the communication complexity of finding a pure Nash equilibrium is 2 to the power n, at least 2 to the power n, just by looking at subclass of games and reducing it to the disjointness problem. Okay? Now, you may think that that comes out because many games do not have a pure Nash equilibrium. Okay? And in fact, one may look, oh, here it's the theorem. Sorry, that's what. Yeah, sorry, that was the theorem I was looking for. Okay, any Nash equilibrium procedure, any pure Nash equilibrium procedure, should say here, requires at least 2 to the power n bits of communication complexity, and the number of rounds you just divide by n.
The game is matching pennies.
No. The matching pennies is, no, we call it the matching pennies reduction because it's a reduction to the disjointness problem using a kind of a matching pennies something. It's just a name. It's not, forget that.
What's the game now?
Well, I give you, there is not one game, remember. Okay. The whole point is that you have a class of games. The whole point of uncoupledness is if I know exactly, if there is only one game we are talking about, then I know what the game is. The whole point is that there is a whole class of games. I can have many utility functions, Yuval can have many utility functions, and any pair of utility functions forms a game. And I want to solve all this class of games. Okay?
And the size of your class is something like 2 to the n, the class you're considering.
Must be. In fact, it's probably even much bigger because the number of games I can have, I have 2 to the power n entries in my utility function. Each one of them can be, let's say, it's a binary game in terms of pair of 0 or 1. So I have 2 to the power 2 to the power n, the number of games. Okay? It's a lower bound. This says that I cannot do it faster than that.
But n is the number
of players.
Oh, the number of players.
If the number of players is n, the number of n tuples of actions is 2 to the power n. Now, a payoff function, a binary payoff function that only gives payoff 0 or 1 is 2 to the power 2 to the n. So that's a number of payoff functions available. So, okay. Okay, now you may think that because games usually will not have a pure Nash equilibrium, that's a problem that, you know, takes a long time to find that there is no Nash equilibrium. So if you restrict yourself to a class of games where it's guaranteed to have a pure Nash equilibrium, namely potential games, if you know what those are, it's okay. If you don't know, those are games that are guaranteed to have a pure Nash equilibrium, and you keep finding those games when you drive back home to Seattle between 5 and 7. Okay, those are congestion games. Okay, traffic. They come up quite naturally, those problems. So with a different reduction, much more complicated, in fact, we can show that the same exponential lower bound holds also for games that are guaranteed to have pure Nash equilibrium. So that's not the issue.
The lower bound, of course, depends on the fact that the utility function of each player is exponential size. There's no way to...
Yes.
Is essentially...
Yes. Now, can you keep this comment in mind and remind me when I start talking about correlated equilibria, where the payoff function is going to be just the same. Nevertheless, I can do much better. So it's not. So it's true that the input is large. Nevertheless, there are things that even with such large inputs, I can get it very nicely. Okay? So, okay.
To have a procedure for potential games means that I know my utility function, and I know that I don't know what the game is that we are playing. I mean, I don't know the other utility function, but I know it's a potential game.
Right. So in fact, there is, let's not get into this. You can read the paper. It's not, I mean, those are details. Okay? I mean, I can spend on each one of the details I can talk about, but believe me, it's not, once you see it, it's not very important. Okay. Now, what about, now suppose that rather than having a big class of games, you have a big class of games with a prior distribution. So you know it's one of those games chosen according to some probability distribution. Then the worst case is still exponential, but maybe on average, on most games, maybe it takes much faster to reach Nash equilibrium. So that's a Bayesian setup. So what we are now assuming is that the payoff function is selected according to some probability distribution. In fact, it's a very simple probability distribution that we are going to give us an example where your utility function is going to be either that or that with probability half each for each a minus I, whatever it says. I mean, it's some nice probability distribution spread out, okay? And it turns out that even in expectation, the lower bound is still exponential, okay? So it's not just that the worst case. There are always those crazy games that, you know, are really pathological, but even if you take a wide distribution over the class of games, the expected number of bits that have to be communicated, so the expected number of rounds it takes until the Nash equilibrium is reached, is also exponential, 2 to the power n. Okay? Now here, there is no reduction. Here one has to use, I mean, here we really have to work from scratch, and the idea there for communication complexity is that each time a bit is transmitted, this splits the set of available inputs into 2. Because that bit could be either 0 or 1, so now we are either, each time we split, yes, we start with all inputs possible, then every time some bit passes through, then this splits it into 2. And you get this kind of what is called rectangular, combinatorial rectangles. There's also no, these things, and you count how many of those you have, and so you have to use some counting of that. You have to see what the probability of having Nash equilibrium is, and there are some estimates there. I mean, this requires some work. It's not just a reduction. Okay, now how about mixed Nash equilibrium? All this was pure. Now mixed Nash equilibrium, there is additional problem, which is the following. Look at this game, where m is a large number. Now this is like matching pennies, except it's, if this would be 1, it would be matching pennies. If this is m, is big matching pennies, big m matching pennies, okay? Now this is a unique Nash equilibrium, which is half-half for the row player, and m over m plus 1 and 1 over m plus 1 probabilities for the column player. Okay? The problem is that if m is a huge number, so if this is the class of games we are talking about, in order for the column player to know what his strategy in equilibrium is, and there is only one, he has to know the value of m. Now if m has 1,000 bits, then he has to get 1,000 bits. Okay? Now that's not fair. I mean, that's correct, but that's not the right counting. Okay? I mean, what I said is correct, but that's not satisfactory enough. Why? Because maybe the game would be, notice, m is something in the payoff function of player 1, of the row player. And it appears in equilibrium in the strategy of the column player. So the row player has to transmit something that only he knows to the column player. He has to tell him what m is. So it requires log m bits or whatever, yes? And that could be a huge number. On the other hand, suppose that you only have 2 games possible. It's either this game or the game with m equals 1. Then, in fact, just 1 bit will suffice in order to transmit whether it's this game or that game. Okay? So this is called encoding. So you have 2 measures. One is the magnitude, which means how many bits are needed to describe the entries in the matrix. And the other thing is the encoding, which means maybe the number of possible values there is small. Maybe the values are huge, but there are only 2 possible values. Then I can transmit it in 1 bit. Okay? So one has to distinguish between those 2 things. Okay? And now here is the result. So there is a family of games such that, so we have to we construct it. I mean, here again, there is some work. Okay? A family of games such that any Nash equilibrium procedure. So now we're looking at a procedure that inputs are the payoff functions. Output, every player has his own strategy which forms part of a Nash equilibrium of the game, mixed Nash equilibrium of the game. And the number of bits that have to be communicated is again 2 to the power n. And this family, again, this doesn't come from the family being a family where the numbers in the payoff function are huge. In fact, each entry in the matrix has at most n bits to describe it, so it's at most 2 to the power n. And in each entry, there are only 2 possible values, which means it takes only 1 bit to say whether it's this one or that one. Nevertheless, the communication complexity is 2 to the power n. Okay? Now, that's again, this requires some work. So, read the paper. Okay. Now, by the way, I should say here that those are lower bounds. If you want to get upper bounds, that is very easy to get upper bounds, which are also maybe not 2 to the power n, maybe n times 2 to the power n, but essentially the same. One way is just broadcast. Each one just transmits its payoff function. Okay? So once you transmit your payoff function, then everybody can compute the Nash equilibrium. There is some rule to do that. Remember, computation has no cost here. Only communication has cost. Another is to do enumeration, just to go cell by cell, and each one says yes or no whether he's best replying, and once everybody says yes, that's it. Those have communication complexity, which are 2 to the power n or n times 2 to the power n of the same order. So you can't do much, what all this says, you can't do much better than just the simple things which are enumeration or random search, exhaustive search, or broadcasting, okay, in general. On the other hand, and you remember your question, right? If we go to correlated equilibria, then, now let's assume that we are looking at games with integer entries, okay? All the payoffs are integer with magnitude at most k. Okay? Then it turns out there exists a correlated equilibrium procedure which is guaranteed to reach a correlated equilibrium in a polynomial in n and k number of rounds or bits of communication. So for correlated equilibrium, you can do it polynomially in n. Okay? Yes. So that's now this is exactly the good point where I'm going to switch to the other thing, and this I want to explain to you also. Because it's a very nice construction. So so let's put this on hold, okay? And let's put this on hold, and let me go here to correlated equilibrium, and I'll use a few minutes just to explain again. I mean, I'll go quickly over things I said last time, but I'll explain this again, and then I'll tell you how this applies to that problem, okay? And then we'll talk about other things, time permitting. Okay, so what is a correlated equilibrium? So you have a game. Here, let me repeat the formal definition. So you have a game. Before the game is played, the players are getting signals. Those signals, so each player is getting a signal coming from some common distribution, from some joint distribution. Okay, signals could be independent, could be correlated. What's important is they do not affect the game. They do not affect the payoff in the game. So they are payoff irrelevant. Okay? So it's like the weather, yes? And I'm not now doing something related to the weather, yes? Or it's like Microsoft stock today, yes? And I'm not holding Microsoft stock, yes? That's, I have to do, what's called, I have to reveal, all interest in my, okay, whatever, yes? So things that are not relevant to the game being played. There are lots of signals out there, yes? Or, what color shirt I came, that's a signal, you can use that. Yesterday I had a different color, that you can take this into account. I don't know, okay? Okay, so Before playing the game, players are getting signals. Those signals have nothing to do with the game. And we are looking at the Nash equilibrium of the extended game with the signals. Now, if the signals do not affect the game, our first intuition says, who cares? Right? Well, that's wrong. Our second intuition is players may care because we can, for example, correlate on those signals. So if it's a nice day outside, we may both play nice, whatever nice means in the game. And if it's, it's a cold day, maybe we are going to be very nasty and go home as quickly as possible. So we can, sorry?
Can you agree on what?
I don't know how, I'm not,
Before you see
I don't care. I don't care. So long as this is an equilibrium, and I'll show you examples in a moment just to understand. I don't care how this equilibrium was reached. Because you could ask the same question. If you have a game with two Nash equilibria, and here is a Nash equilibrium, why are they playing this one and not that one? Battle of the sexes. Why are they playing this Nash equilibrium, not that Nash equilibrium? I don't know. But this is an equilibrium. That's what I say. How did they reach it? I don't know. That's what all the dynamics are coming to tell us. But this is a static concept. A static concept that says it's an equilibrium. An equilibrium where what players are doing, as a function of the signal, they can use the signal in order to decide whether to play top or bottom or left or right or whatever. Okay? So let me jump immediately. Okay, here's an example. Okay? So that's a chicken game. Okay? Which, the two cars driving one towards the other. And so if they both stay on course, there is a big crash, which is quite bad for both of them. If this one stays and the other one leaves, then he is the macho and this is the chicken, and here the other way around. And if they both leave, well, they are both alive, and they both left, so it's less than you stay than the other anyway. So don't take those payoffs seriously, but this is the game. Okay. Now this is a Nash equilibrium. Okay, because the row player, if he moves up, he loses 1. The column player, if he moves here, he loses 3. So it's a Nash equilibrium. Here is another Nash equilibrium. Those are two Nash equilibria, okay? Here is a publicly correlated equilibrium, which you can interpret the following way. So they toss a coin, or a coin is tossed. A coin is tossed. If it comes heads, then they both play this cell, bottom left. So the first one stays and the second one goes out. And if it came tails, then number 1 goes out, the row player goes out, and number 2 stays in. So that's a way which, so for example, they can correlate, they can decide before the, nobody has to know, yes? So they can correlate on, on the second at which they started, or on the weather, or on the color of the shirt of the lady that was the first one on the left, which one, I don't know. They can have various correlation devices like this, but something like this is the correlated equilibrium, okay? So there is a random signal, this or that is probability half-half. If the signal is this one, then they both play here. If the signal is this one, they both play here. That's a correlated equilibrium, which is just a convex combination of two Nash equilibria. Okay? And that's what's called a publicly correlated equilibrium because it's a public signal. Now, if that's all it would be, if that's all that correlated equilibrium would give us, just convexifying the set of Nash equilibria, that's nice because convexification is always a good thing. But, a good thing, for proving theorems or for doing things and so on, but it goes beyond that. And here is another correlated equilibrium. That's an interesting correlated equilibrium. So assume that, so let's think about the following scenario. There is a mediator, a black box or something, a mechanism. What that mechanism does, chooses one of these cells according to these probabilities. So in fact, chooses one of these good cells, doesn't choose a 0, 0. With probability 1/3. Okay? That's what the mechanism does. Then what the mediator, let's call him. Then what the mediator does, suppose that this was a cell that has been chosen. Then the SL, okay? Then it tells privately to the row player S, which corresponds to stay. And it tells privately to the column player leave. Okay? So if this is a cell, row player gets the signal stay, column player gets the signal leave. If this is the cell, both players get the signal leave. If this is the cell that was chosen, the row player is told leave, the column player is told stay. Okay? Now, given those signals, I claim that it is optimal, I claim that it is a Nash equilibrium for the players to follow what the mediator told them to do. And let's check that. Let's assume that I'm the role player and I've been told stay. I've been told stay, then I know that stay, it comes only from this cell, yes? Because here I would here leave. So I'm told stay. So it means that that was the box that mediator chose. That means that the other guy must have been told leave. Now, I want to show it's a Nash equilibrium to follow the recommendations. That means assuming the other guy follows the recommendation, assuming that the other guy leaves, what's best for me? To leave or to stay? Answer, to stay. Because stay gives me 6, leaves give me 5. So I stay. That's easy. Now assume the mediator tells me leave. Then I say, aha. That's always good to say aha. Let's think, what does it mean? It means that it's one of these two cells. Right? This is the third, one of these two cells. Since they were equally likely, then I give probability a half and a half, conditional probability half a half, posterior probability half half, that it's this cell or that cell. Which means the probability that the column player was told to leave and to stay is half half. If the second player, if the column player follows his recommendation, I'm checking whether I should also follow mine. Well, if he follows his recommendation, he plays leave and stay with probability half half. So with probability half, so if I play leave, I'll get 5 and 3 with equal probabilities, which is 4. If I play stay, I get the average of 6 and 0 with equal probabilities, which gives me only 3. So stay is better than, so leave is better than stay, so I should also follow the recommendation. And the same thing for the second player. So this is the correlated equilibrium, which is not a mixture of Nash equilibria, because notice how it is. It is not a product measure. Yes? It's not an independent measure. It's not a product of some marginal here times marginal here because of this 0 here. And in fact, if you look at the payoff here, you get something like 14 over 3 for each player, which is much larger, which is larger, not much, which is larger than any Nash equilibrium. So in fact, it's outside the convex hull of Nash equilibria. It Pareto dominates. It's a Pareto dominant outcome here. Okay? So there are correlated equilibria where the correlation is a subtle correlation. It's a real correlation. It's not independent correlation. So now going back to, okay, so now going back to, in fact, okay.
Leave state was not part of it.
Leave, okay, there is a mixed Nash equilibrium here. There is a mixed Nash equilibrium that gives positive probability to all 4 cells. There is something, 2 sevens, 4, 5, 7, something, I don't know. You can compute it, yes? So it does appear, but there is no, but it always appears together with a 0, 0, and in fact the payoff is quite low. It's lower than, say, those two, the average of those two. Notice the average of those two is 9 over 2, it's 4.5, and 4.5 hopefully is less than 14 over 3, if I did it correctly.
Not very much.
1/6, but you know, multiplied by 1,000,000 because those are millions, you know. Of course, I mean I can make any difference I want. You realize that, yes. Just okay. So so if the signals are independent, so if my signal and the other player's signal are stochastically independent, that's just a Nash equilibrium. If the signals are public, like what's called sunspots, yes? So we're all looking at the sunspot. The sunspot is a good thing that unless I am in telecommunication, really doesn't affect anything. Maybe also in telecommunications nowadays, I don't know. Do sunspots still affect our phones or something? Probably not. But okay, most of the things we do, sunspots don't affect them. We can condition on that. That's a public signal. Everybody can see the sunspots. Then you just get a convex combination of Nash equilibria. Butterflies, I won't tell you. That was, you missed it if you were here, you weren't here last time. Boston Celtics, I won't tell you, but those are nice examples. Okay, so it's also just real-life examples of correlated equilibria. And anyway, what's important is the following, which people don't realize. Signals are all around us. The weather, the newspapers, we all have those signals, private or public. Now, if we have signals, they'll find their way in equilibrium. They're unavoidable. So talking about Nash equilibrium is like saying you are in a world without signals, or you are in a world where all signals are statistically independent. I don't really know of such an environment. Even in the lab, when you put people, they still had the same newspaper or heard the news in the morning or saw the weather. So there are correlated signals. I don't know of any environment you can guarantee that there are no correlated signals that players have before playing the game. So in fact, correlated equilibrium is a very natural concept. Okay? Now, there is a beautiful theorem of Aumann. By the way, the concept of correlated equilibrium is Aumann 76. I think so, yeah. Yeah, 76 was a good year. Agreeing to disagree was also 76, yeah? Or maybe this was 74. 74, sorry. Okay, well, within 2 years. So here's the following nice result that, wow, okay. That if all players are rational, what does it mean rational? Rational means you do not play something that you know for sure is bad for you. One can write this nice in an epistemic model. In fact, it's a very weak form of rationality. And so if everyone is rational, and everyone knows that everyone is rational, and everyone knows that everyone knows that everyone is rational, which means the rationality of the players is common knowledge, then they must be playing a correlated equilibrium. In fact, it's if and only if. There is here an assumption of common prior, for those that know a little about epistemic models. But in some sense, if you are talking about the highest degree of rationality, so that says everybody is rational, and this is common knowledge. I mean, this is really far out. Yes, that's very heavy. That's correlated equilibrium. So correlated equilibrium embodies rationality to its fullest. Okay. By the way, I'll come back to this point. The set of correlated equilibria, in fact, once you write down the conditions, is just a nice convex polytope given by a finite set of linear inequalities, which I've written them here. Doesn't matter what they are, but there is a finite set of linear inequalities. It's not like Nash equilibrium, which is a fixed point. Okay? Of multilinear maps, but still, of a multilinear map, but still, it's a fixed point. This is just a convex, a nice convex polytope. Okay. Now, you know what?
So if we have common knowledge of rationality.
Well, the if and only if means that if you describe the thing correctly, yeah, the if and only if means relative to that model, which means common knowledge of rationality implies correlated equilibrium. That's easy. The other direction is that any correlated equilibrium, you can find a model where there is common knowledge of rationality and where this is played. Okay? That's what this means.
What do you mean you can't find a model?
Well, in a different model, there may be a different correlated equilibrium. So for each game in correlated equilibrium, I can write an epistemic model. A model means a model of knowledge. So you have players, you have knowledge operators, you know what people are doing, you know what the actions are, and you have to write a syntactic or syntactic, whatever model of knowledge. Interactive epistemology is the whole area, which says it's not just one player that knows, but it's many players that know, and each one knows something about what the others know or don't know, about what he knows or don't know, and so on. And after two such iterations, you get completely lost unless you start doing it formally and nicely. Okay?
But take the case that everyone knows just the whole game and all the others. How would you somehow decide how to reach this correlated equilibrium? I mean, it's not clear.
No, it's not clear. Again, this is an equilibrium kind of result. It says if we are in a situation where all players are rational, if we are in a situation, I don't know how they reach that situation, but if we are in a situation where everybody is rational and that is common knowledge, then that must be that they are playing a correlated equilibrium of the game. Period. That's it. Can't be anything else. Now, how do they reach such a situation? I don't know. That the theorem doesn't say. Okay, all these are static results, equilibrium results. Okay. Okay. Now I want to tell you about. Now let's go back to communication complex and so on. So here is the connection. Do correlated equilibria exist? Why?
Nash equilibrium.
Because Nash equilibria exist, and the Nash equilibrium is a special case of correlated equilibrium. How do we prove that Nash equilibria exist? A fixed point theorem. So we are using a fixed point theorem to prove that a nice set of linear inequalities has a solution. That's an overkill. It's a mathematical overkill. Yes? We don't like that. Question, is there a simple proof, a linear algebra proof, a linear proof, okay, that the set of correlated equilibria is non-empty? Okay? Well, that turns out not to be an easy problem. In fact, Aumann was for years saying, where is such a proof? Was looking for such a proof. And so David Schmeidler and me, in sometime in the late 80s, we found such a proof. Okay, and I'll tell you, and that connects to everything that I'm going to talk later. So I'm going to tell you. Now that proof essentially did the following: took the set of linear inequalities here, and applied linear duality. In fact, I had to apply linear duality twice. There was a double application of linear duality. It's not twice to get back to primal. It was inside a sub-problem to which you apply another linear duality. But, and that's a nice, that again, it's something that, unexpected. We decided, well, it's a game theory paper. Rather than using linear duality, or, you could use lots of other things, let's use the minimax theorem. If you have been in my last talk, you saw how nicely one can use the minimax theorem. For everything player 2 does, I have a response, then I have something that, okay? So then what we did, we defined a nice auxiliary problem, okay? A two-person zero-sum game, okay? Where we had here an auxiliary player 1 and an auxiliary player 2. And player 1 here was choosing an n-tuple of actions in the original game. So it's like choosing a strategy combination for all the players in the original game. And player 2 here was choosing, I'll write this in words, recommendation plus deviation. So in order to check that something is a correlated equilibrium, you have to check that for every recommendation that the mediator gave you. So the story with the mediator, okay, sorry, I have to backtrack. The story I gave you with the mediator, 1/3, 1/3, 1/3, is general. Namely, there is something called, that's a canonical way to describe every equilibrium. You can always do it in such a way. That's an easy exercise, okay? So think of a correlated equilibrium like a mediator chooses a cell in the matrix and tells player 1 what row, tells player 2 what column, tells player 3 whatever coordinate he chooses, okay? And everybody is going to follow what the mediator says. If this is an equilibrium, then the whole thing was a correlated equilibrium of the original game, okay? So in this representation, to check that something is a correlated equilibrium, so what's a correlated equilibrium? If here I have all the n-tuples, the cells, these are the cells in the game. So correlated equilibrium is just a probability distribution over this thing. It's like a mixed strategy here. How do we check that something is a correlated equilibrium? Well, we check for every recommendation of the mediator to a player and every possible deviation, whether he wants to follow the recommendation or not. So we look at the payoff if he follows the recommendation, minus the payoff if he doesn't follow, if he deviates, and we want to make sure that this is always less or equal 0, or greater or equal 0, depending what I said. It's the right sign, okay? Deviation is worse than following the recommendation, okay? Now, okay, so it turns out that there exists a correlated equilibrium if and only if there exists an optimal strategy of 1 guaranteeing 0. Okay? If you can guarantee, no matter what recommendation deviation there is, that the payoff is greater or equal 0, means you never want to deviate. Never want, it's true for all players. Okay? In the right way. So there is here an auxiliary game. So there is this auxiliary game where payoffs are defined in the right way. Okay? And that by the minimax theorem is if and only if for every strategy of 2 there is strategy of 1 with payoff greater or equal 0. Okay? That's a minimax theorem. And we prove that. In order to prove that, by the way, there was another minimax theorem inside here. Okay? But that gave this proof. Everything is linear programming. Everything is linear. I mean, the standard things. Now, this game, in fact, led us to all the dynamics that I didn't talk about, and I see I won't have time to talk about. But I'll tell you something else. Let's go back to communication complexity. Christoph Papadimitriou, has a nice work where he shows that you can compute a correlated equilibrium in polynomial time for certain classes of nice games. Anybody has seen this paper? Appeared in one of the conferences, I don't know. Okay. So his idea is the following. he starts from this game, okay, from this auxiliary game that we build, okay? And from this auxiliary game, he says, I want to find a solution to all these greater or equal 0. Okay, something that will, the primal problem here is to find here a vector here such that in each column the payoff is greater or equal 0. So what he does, he looks at the dual problem and start constructing using ellipsoid method. Okay, I won't tell you all the details because I don't know them. I mean, I once more or less understood what he's doing, but there is a nice construction where he has a polynomial number of steps of the ellipsoid method that he works on the dual problem, and every time, what happens every time, he gets here something which is a product distribution. A product distribution means like a Nash equilibrium, what we have in a Nash equilibrium, okay? And the end of that, since this has a solution, this problem being unfeasible, when the ellipsoid has become small enough, given the precision that he knows, given the numbers, given the payoffs, then he knows how many steps he has to use. After a certain number of steps, the ellipsoids are so small that he knows there are no longer solutions. Then he takes all the primal variables, which were the dual of the dual variables that he obtained along the way, and he knows that in the convex hull of those there is a correlated equilibrium. That all comes out from this construction. And that all these things can be computed in polynomial time in whatever is relevant there, provided one thing, provided that you can compute the payoff, okay? Provided that you can compute ui of, let's call this x1, x2 up to xn. So this is a mixed strategy of player 1. This is a mixed strategy of player 2 and so on. So you have an n tuple of mixed strategies, and you need to compute what the payoff of that is. That's all that is required. So he has to talk about the class of what he calls polynomially succinct games, or succinct polynomial games, or something of that sort, okay? Which are many classes of interesting games where you can compute the payoffs in polynomial time for those things. And if you can do that, then the whole computation of correlated equilibrium becomes polynomial. Okay? It's quite a clever, it's a clever construction, a very nice construction. Okay?
Are there payoffs you're interested in that you can't compute polynomial time?
Sure. Remember that if this is say half, then you have to take 2 to the power n average of all the entries in the matrix. Now that's an exponential number of entries that you have to compute their average. That's not polynomial. Okay, if you find a better way to do it, I mean, go ahead. I mean, there are still lots of open problems there. So, okay, but the point is that you want to be able to do this in polynomial time. Okay, now approximating that's again depends what kind of approximation, so on. Okay, okay. Now coming back to our communication complexity. In our setup, computation is free. We don't count. There is no cost to computation. There is only cost to communication. Remember, each one only knows his own utility function. Now, what happens is this. The steps of the algorithm of Papadimitriou can be computed locally by each one of the individuals. In fact, there is a universal construction that goes from this variable to this variable. Okay? So they can all compute it. So they know at each step they get something like an n tuple of mixed strategies. Then what is needed for each one to know what the payoff of each one is for those n tuple of things. Each one makes his computation on his own because he knows his own utility function and has to transmit it. Now transmitting the expected value, that only if all the numbers had k bits is only k bits. So the whole thing is polynomial and the number of steps is polynomial, so the amount of communication is polynomial. And you can do it now. Now the whole point is that for computation purposes, you needed the computation of this to be polynomial. So you needed special classes of games. For our purpose, the computation of this has no cost, which means we can allow any game we want, and we only count the number of communication bits, and that's okay. That is polynomially bounded, so this applies to any game. Any game that the payoffs are bounded by, let's say, a certain number of bits. Okay? So that's a nice way to take that into the communication setup and to see how you can get exact correlated equilibria, not approximate correlated equilibria, but exact correlated equilibria with polynomial communication complexity. Okay?
Somehow I don't see anybody actually playing this game in this way, but
Remember, those are bounds. Okay? So that, again, the lower bounds for Nash equilibrium says, listen, you can be as smart as you want, and you can invent your own way for them to reach a Nash equilibrium. You cannot do it less than exponential. There is no way. That's what communication complexity lower bound tells you. Now, then you come and said, well, okay, I mean, that's, of course, the data is exponential, it's double exponential, whatever, so of course I need exponential. Then I say, yes, you need exponential for Nash. For correlated, I can do it polynomially. So it's not a property of the problem that the input is so large. Even with such a large input, I can get an output in polynomial time. If the output is nice, correlated equilibria, I can get it in polynomial time. Nash, polynomial communication complexity, yes. So the number of bits that have to be transmitted is that. So the number of bits or the number of rounds it will take, that's the same thing up to the factor of n, yes? So that's quite a, okay. Now, okay, now I want, okay, so what I will do, let me take 10 minutes or so, I will jump, okay. Okay, let me jump to this. This is an it's a full page ad from Haaretz. And some of you know what Haaretz is. Oh, I mentioned Haaretz last time about this. So your opinion of Haaretz probably changed a little after I told you about this horse stable equilibrium. It's the same newspaper. Anyway, that was a full page ad, okay, which I translate freely, yes. In Hebrew, that was Zvita Balev, okay. Zvita Balev, that's a pang, that's really, your heart misses a beat. Don't you feel a pang of regret? Look, this XYZ, now don't go and look, there is no XYZ on any of the known markets, yes? So it's some remote, I don't even know what it was, some crazy thing. Okay, this XYZ in this period, which is of course a randomly chosen period, yes? Its yield was 47.15%. Same time, the Nasdaq was 18%, the Dow Jones 4%. I mean, come on, don't you regret not having invested in XYZ? So don't wait, run to your broker, right? And he's going to be broker, by the way, at the end. Not the broker. More broke. Who's going to be more broke? Yes. Okay, now that's a standard ad. In fact, open, the Wall Street Journal, open any journal, you'll see ads like this, okay? So they tell you, listen, I mean, don't you regret, look how nicely this has worked, look at what those things are. So go and switch, okay? So let me define a dynamic. So that doesn't suggest, that was just a nice illustration for a following dynamic, which we call regret matching. Now, this is work with Mascolel, with Andreu Mascolel, what I'm talking about now. I didn't show you the beginning, but was there someplace. So what's regret matching? Regret matching says the following. Every period I have to make a decision. Should I switch to this XYZ, or should I stay with whatever I have invested in? Okay? So the rule is the following. I'm going to switch next period to a different action with a probability that is proportional to the regret for that action. What does this mean? Let's make this more precise. So the regret is by how much my payoff would have been higher had I made such a switch. Okay? So if that was, 47% versus the Nasdaq 5% or versus the Dow Jones 5%, I have a big regret, yes? But if the other thing would have given me 45% and this gave me 47%, well, my regret is 2%. I don't, maybe I'll switch, but my probability of switching will be much smaller, okay? So now if you want to see the formula, to make this precise, so let U be the average payoff up to now, so I'm at some period T. Let VK, think of V as virtual payoff, so K is another action. So let's say that J is the action I'm currently playing, last period, that's what I played last period, and I'm considering switching to a new action K. And I'm looking at the average payoff if I make the switch from J to K. Now, I can do this just in last period, but since we are talking about long term, making a change in just one period will not affect much my payoff. So let me make let me make some other computation. Every time I play J in the past, I'll replace it by K, and I'll change nothing else. Now that's of course in a game it's quite stupid, because if I change things in the past, then the whole thing would change and so on. But again, that's something I can compute. So let's compute that. It's a simple rule for computing regret. Okay. And so that's what I would have gotten had I played K. That's what I actually got. The difference is the regret, and I take the positive part. If this is bigger than that, the difference is the regret. If this is smaller, then I have no regret. The regret is 0. Okay? If I got 7, and if I would have switched, I would have got 6, I have no regret. Okay. If you want if this is the formula, okay. In fact, it's very easy to, it looks like a complicated formula, but you can recursively compute it very easily. You update it every time. You just, okay. Okay, let's not get into the details. I'm sure you can reconstruct it. So now the strategy of regret matching says the following. Switch next period to a different action K with a probability that is proportional to the regret. Okay? And with the remaining probability, stay put. Do the same thing. So that says that sigma of K is the probability of playing K, the probability that player I at time t plus 1 plays K. It's some constant times the regret of K. And 1 minus the sum of those things is the probability that it stays put. And the constant is chosen once and for all so that those things are indeed probabilities. So those things add up to less than 1. Strictly less than 1, in fact. It's important. Okay? So here's the theorem. Arbitrary n-person game. Assume that all players play regret matching. Then the joint distribution of play converges to the set of correlated equilibria of the game. That's arbitrary game. Okay?
To any point.
Right. So joint distribution of play, again, it just counts. Yes, so we already, okay. Joint distribution of play just counts how often I'm playing, each cell has been played. So if it's this two-player game, so first period they played here, then that's a joint distribution of play, put a 1 here. Next time they played here, so it's half here, half here. Next time again here, so it's 2/3 this cell, 1/3 here. So I'm just looking at the empirical distribution, okay? And notice, okay, that's very important. People miss this point. It may be that every time my randomization and Yuval's randomization are independent. Yes, Yuval is my opponent throughout these talks. Yes, he's sitting here next. Okay? So even though we are playing independently every period, that does not imply that the joint distribution here is going to be a product measure. Because that says conditionally independent given the past every period. So that gives you an arbitrary distribution. And in fact, that's a trivial point, but people keep looking all the time at marginals, which is clearly wrong. It doesn't have the whole information. Okay? Oh, it's written here. Yes, I knew it. Yes. Okay? In fact, players observe this, and the story I always tell here, now that's really a behavioral observation now. People react to joint distribution. So suppose Yuval and me are playing matching pennies. Okay, matching pennies, half-half is the optimal strategy. And, you know, over time I see that I'm playing, that each one of us plays about half-half heads and tails. But then I notice, suppose that I'm player 1, I'm the matcher and he's the mismatcher. Every time I played heads, he played tails. And every time I played tails, he played heads. But that's still half-half of the time. Then my reaction, you know, after, okay, where's the mirror or something? How does he know? Yes, he must have some. So the fact that the marginal distribution is half-half for each one of us, that's not the whole story. The whole story is what is a joint distribution. Okay? And that's very important. We react to it. I mean, that's something we should take into account. And surprisingly, we do, lots of models just, not to say most of the models, just ignore it. Okay? Most of the models, say 10 years, up to 5 or 10 years ago, they completely ignored these things. Even all the experiments that were done, they had the data of how often each cell has been played, and they just threw it away and just looked what frequency player 1 plays top and bottom, what frequency player 2 plays left and right. They completely ignored the correlation between those things, which is very relevant, as I told you in this game, yes? The matching pennies. Okay. Okay, so now this I can jump. Okay, this I can jump. Okay, so, formally the theorem says that if I look at the joint distribution of play, namely what's the frequency of each cell, that the distance between that and the set of correlated equilibria, which remember it's a nice convex polytope, converges to 0 almost surely as t goes to infinity. Does not converge to a point, converges to the set, which means in fact it gets into the set, it can go out, but from some point on it's going to be in an epsilon neighborhood of the set, or if you want it's going to be a correlated epsilon equilibrium from some point on. It's almost sure convergence, yes? Okay, the proof it goes through Blackwell approachability, which I won't talk about because I already did. So, okay, so I'll jump that. Approachability remarks, okay. You know what, I don't have time, so let me jump over all this, behavioral, okay. So let me now go, okay. Okay, so we have a nice dynamic. This regret matching goes to correlated equilibrium, okay? Good, that's nice, okay? There are some other dynamics converging to correlated equilibrium. One of them is conditional smooth fictitious play. It's something quite complicated. It's quite complicated. It's taking fictitious play, conditional, smoothing it out, computing an eigenvector. It's a complicated thing. But you can show that it also converges to correlated equilibrium. Regret matching is something, is a very simple rule. Yes, you just adapt very easily from period to period. Okay? So regret matching, just to remind you, said that the probability sigma stands for probability of playing k was proportional to the regret for k. Now let's look at more general functions, which is that the probability of playing k is some function of the regret. Now what kind of function? Well, I want a sign preserving function, which means if regret is 0, I don't want to play it. If the regret is positive, I want to play it. And I want it to be a continuous function. In fact, Lifshitz. Again, I'm not giving you the general conditions. I'm giving you simple conditions that fit on a half a slide. Okay? And as you can see, I've missed here monotonicity. It's not because there is no space on the slide. It's because it's not needed. Okay? F doesn't have to be monotonic. Just have to be a function that is continuous at 0 and is positive, and 0. Okay? So for example, instead of, so standard, okay, I'll give you an example in a moment. Well, theorem, instead of playing proportional to the regrets, you just play some function like this of the regrets. In fact, different people, different players play different functions, and in fact can be much more general than that, and I'll tell you in a moment the mathematics of that. The same theorem applies. So I can play proportional to the regrets. Yuval can play proportional to the regrets to the power 7. Okay, somebody else can play something that is, I don't know, proportional to the sign of the regrets, or, no, I need positive. It's okay on the, whatever. Okay? So that, by the way, has appeared already in 2004. Okay? So here are some examples. So proportional to the m's power of the regrets, so when m equals 1, it's regret matching. When m goes to infinity, this turns out to be essentially fictitious play. For those who know what fictitious play is. Fictitious play says you look at the empirical distribution and play the best reply against that. Okay? So as m goes to infinity, you get essentially fictitious play, or the thing. Problem with fictitious play that it's not continuous. Small change in that thing, then the best reply jumps. Discontinuity is not good. Okay? Namely, destroys the result. So it does not work. However, if you smooth it out, then it works out. Okay? So that's what leads to this smooth fictitious play. So in some sense now all those results I talked about now belong to one big pile. Okay? There is a big class of dynamics, all of them work. And the idea, now let me tell you something about the geometry of that, because that's something very nice, which sorry?
Is it the theorem doesn't hold for the non-continuous?
No. So I'll tell you where it comes from. It comes from Blackwell. So Blackwell said the following. Here I have a set C that I want to approach. Okay? And if you remember what I talked last week, the Blackwell, so if the set, assume the set is approachable indeed, satisfies the conditions of approachability, then the Blackwell strategy said the following. If the average payoff is inside, then play arbitrarily. But if it is outside, so this is the average payoff at period t, then what do? You find the closest point here in C, you draw the supporting hyperplane, you know by assumption that this whole half space is approachable, you know by assumption, that was the approachability condition, that there is a way to guarantee that next period payoff is going to be someplace here on this side. and that's what you play. And that will work. That will make, in a sense, the new average. The new average is going to move when t is large enough a little bit in this direction, which means the distance is going to go down. And the one-line computation shows that this works. That's Blackwell's strategy. That's what leads, after 5 iterations of changes and so on and so on, but that's essentially what leads to regret matching. Here's the question. How robust, or how strict is this construction? Now, of course, if instead of playing for this half space, I'll slightly tilt it, should work if my slightly tilted is small enough. But it looks like the proof of Blackwell is one of those proofs where everything fits right. You look at the computation, you know, everything is beautiful there. So the first intuition is that's what you can do. But let's ask the question. Suppose I want to do the following. Is there another color? No. Okay. So imagine this is another color. Okay. So now let me make another picture. So now I have again my set C, and this is what I went. Suppose I have a mapping that tells me for every point here what half space to use. This says use the half space determined by the closest point. But maybe I want to use this half space. So suppose I have a rule telling me for every point x here, I have here something, let's call it lambda of x, which is a normal. So the moment you give me a direction, I'm going to put the half space in that direction that is just tangent to it. Okay? So this is the rule that for every point gives me the direction of the closest point. But suppose somebody gives me a mapping, lambda, so there is a mapping lambda that associates to every point outside a direction. And suppose I'm going to use such a lambda strategy that says every time my average payoff is here, I take the lambda of the average payoff, construct the half space. By assumption, I know I can guarantee next time payoff is here, and that's what I'm going to do. For what lambdas am I going to guarantee that I will approach? Oh, I guess, no, suddenly I had myself double. I think this also. Okay, so for what mappings lambda is it guaranteed, no matter what the other players are doing, that my average payoff is going to converge to a set C? So here is a nice theorem. Turns out that the following, okay, so what you need are 3 conditions. 1, lambda is continuous. 2, what you need is that the point and the set should be separated, because if you are taking a half space, like this, then in principle you can stay put all the time. Okay? So that means that lambda of x times x is bigger than the supremum lambda of x times c. Okay? So it separates. And the third condition, lambda has a potential. So that this lambda is the gradient of some real valued function, a C1 function there. And so that means it's an integral. So if you look at this as a vector field, so if you think of this, so if I put the lambda of x at x, and you think of a vector field here, that's an integrable vector field. And it turns out that those 3 conditions suffice, and in fact, they are, without either one of them, immediately get a counterexample. Okay? So without any one of those 3 conditions, so without continuity, which again, that's why fictitious play doesn't work. When you have jumps in those dynamics, that kills you. Okay? And without this is clear, and without the potential also, you can start going around in circles. Okay? So the potential somehow gives you a nice Lyapunov function that things work. Now, the nice thing about this is that when you take this and translate it to the problem, it gives you, those that I wrote down there are particular cases. But it's a much wider class of dynamics that you get from this kind of construction. In fact, you can replace, for instance, something that you could immediately think about, which is what started us in all this. When he said find the closest point, you find the closest point in Euclidean norm. Now, why Euclidean norm? Who cares? Why not the LP norm P equals 17? The geometry there somehow shouldn't depend on what norm you are using. On the other hand, the Blackwell inequality talks about the L2 norm. So it fits. But somehow the intuition is that the geometry there should not depend on the norm. And in fact, that's a right characterization. So this, in some sense, characterizes the kind of strategies that work no matter what the problem is. Okay? Universal, what we call universal approachability strategies. And that gives you a wide class of dynamics that include everything I wrote here, and there are many more that I didn't put. Okay? So that's a nice, okay? And final thing, okay, that will just to give you something surprising, okay? Suppose I am not in an uncoupled situation. I don't know the other people's payoff function, but I know my own payoff function. And by the way, regret matching and all these things are uncoupled dynamics, because what I look is what everybody did, and I compute my regret using my own payoff function, what I got versus what I could have gotten. Okay? It's uncoupled. Very nice. Okay? Now suppose I'm in what we call the case of the unknown game. What's the case of the unknown game? That a player is only told what the set of actions is. So I'm told you have 3 actions. And I'm asked, okay, play. I say action 2. So I see a bzzz. You got 7. Okay. Now play. Action 1. Okay, you got 3. That's it. So every time I have to choose an action, I get back a number. That's all I know. Nothing else. I don't know if I'm playing against a machine, against nature. I don't know if I'm playing against Yuval. I don't know if I'm playing against 10 players.
We get when we were born.
The veil of ignorance, if you want, yes? That's behind, yeah. So we still don't know anything, right? I have no idea. It's just there is this machine out there that I put as input my action, and then comes back a number. That's your payoff. I have no idea where it comes from, okay? Let's assume, however, that it is an n-person game. And indeed, the machine that runs the game computes the payoffs, so he has n players like this, each one knowing only the actions that they have, and what they did in the past, and what their payoffs were. So they don't know the game, they don't know what they don't know if there are other players, how many there are, they don't know the payoff matrix, they don't know anything, okay? Now, if the game is unknown, they cannot compute regret. How do I know what I would have gotten had I done something different? I mean, I don't know. For this, I have to know my own payoff matrix to say, instead of this, I get this. So I cannot compute regret, okay? I can compute proxy regret. What's proxy regret? I want to know what I would have gotten had I played K instead of J. So let's see what I got when I played K. That's all I have. I mean, I'm sorry, but that's all the information I have. What can I do? Okay? Now, you have to normalize this slightly, because if I play K much more often than J, then I have to divide everything by the relative probability, okay? Theorem. Assume everybody plays regret matching relative to proxy regret. Then the joint distribution of play converges to the set of correlated equilibria of the game. So, just think about this. You have those players out there. They're playing a game, but they have no idea. Each one only receives, plays an action, and is told what payoff it is. Okay? And they keep playing. But they are playing regret matching according to this proxy regret, which is not even an exact regret. And after some time, I come and look how often each cell in the matrix is being played. And I see it's approximately correlated equilibrium. Quite surprising, yes? Yes, it's quite, what happens here is that, in fact, the difference between the regret, the actual regret, which they cannot compute, and the proxy regret is a martingale with 0 expectation. Because that's what those probabilities do. So once those converge, but it takes a lot of approximations and some nice work. That's, by the way, it's based on an idea of Dean Foster. So he and, I think he and Vora used it for some in some other setup, and he said, oh, you can use it here. I said, no way, this can't work. That was my first reaction, which I'm sure is yours also. But okay, so uncoupled dynamics I talked about, and
Think about the rate of convergence.
the rate of convergence in all these things is polynomial. Correlated equilibria are nice. Okay. Now, one point that it's important, and that's my last comment, and I'll connect it. I said that correlated equilibrium is a nice convex polytope. However, that lives in the simplex of n tuples of strategies. Okay? So I look at the action combinations, at the strategy combinations. So like if I have n players, each one has a binary choice, I have 2 to the power n vertices. I look in that simplex, it's a distribution there. Now, to reach a convex polytope there, I mean, why don't we apply simplex method or any of those linear programming things? The answer is because it's not uncoupled. The answer is that requires all players to move together. It requires you to adjust the n-tuple of strategies at once. That's not good. Okay? Now, when we wrote this paper, we didn't have the notion of uncoupled. I think we said we want to decouple them. Yes, there was a previous version, but we were aware about this thing. So if you just want to compute a correlated equilibrium for a known game, sure, you can just apply linear programming or whatever. But you want to do it in such a way that each one of the original players plays separately. Okay? Plays separately. Now the question is, what does it mean? So natural conditions say he only knows his own payoff function. That's uncoupledness. But you can get correlated equilibrium with such nice and simple dynamics, what we call adaptive heuristics, you can do it nicely, simple dynamics, fast, and furious. What's the name of the movie? I don't know. Okay. On the other hand, Nash equilibrium. So what's the moral of this? So what all this sits? Yes. Correlated equilibria. There are nice ways and quick ways and good ways and polynomial ways and whatever you want ways to get to them. They are not always easy and they are not so on. But Nash equilibria, it's exponential. It's difficult. You need exhaustive search. You have to work hard. It's a fixed point. All these things. So you see this from very different angles and from very different things. It's not surprising. But nevertheless, some of these things are quite delicate. And there is now a whole literature out there on dynamics, converging to Nash, converging to correlated, and what kind of dynamics do that, what kind of dynamics do that, what are they do. And some of those correlated dynamics, by the way, relate very nicely to all this behavioral literature. In fact, all this regret matching is a close cousin of things that have appeared in the behavioral literature, psychological experimental literature, except that for this, we have results. For those, there are no mathematical results, no theorems. Here, we have nice theorems of convergence. The other things, which are very similar, are quite close, but not so much. So I think that that's just. It's beyond my time already. So.